everyone, and thanks for watching Edupedia World Videos. In the previous few videos, we've learned essential concepts like center of mass and the basics of rotational mechanics. We strengthen our knowledge of these concepts now by looking at how they're applied to various problems. Let's start with the standard problem. I have two blocks, one of mass small m and the other of mass capital M. They are kept on a smooth floor, that is, it's frictionless. And what we've done is initially the spring is at its natural length, but we compress the spring by pushing both the blocks together, right? So the question, it's given that we've compressed the spring by a distance x. Now x is not the length of the spring. This is the first mistake which beginners make. X is the compression, that is, it is the change from the natural length. If the natural length was L, now the length is L minus x and the compression is x, right? So we compress them both by a distance x. Sorry, we compress them both such that the sum of the distance is x, and then we release them. So obviously the spring will apply a force towards both of them outwards as it will try to regain its natural length. And what we are asked is, what is the velocity of both of the blocks when the spring regains its natural length, right? So initially the spring is compressed by a distance x and both the objects are at rest. So energy initial will be, I'm taking this combined thing as a system, that is the small mass plus the capital mass plus the spring. So the kinetic energy of the two blocks is 0 initially. The spring has a potential energy of half kx squared, right? What is the final energy? My final situation will be when the spring has achieved its natural length, and at that point it will stop pushing the blocks further and the blocks will lose contact with the spring, right? So in that case, let's say that time this has a small velocity v and this has a velocity capital V, right? So E final will be half small m v squared plus half capital M v squared, right? And by conservation of energy, this has to be equal to E initial, right? So in the question we were given both the masses, we were given the spring constant and we were given the compression. We needed to find out the speed of each of the individual blocks. So we have this equation, half mv squared plus half mv squared equals half kx squared. That is one equation, but we have two unknowns, small v and capital V. We know from basic mathematics that if we have two unknowns, we need a minimum of two equations to be able to solve them. The second equation we can get from conservation of momentum. Remember, the first equation was conservation of energy because no external forces are acting, and that also implies the conservation of momentum. Initially the momentum was 0 because the spring has no mass. The spring will always be assumed to be light unless mentioned otherwise. Both these masses are at rest, so initial momentum is 0. Final momentum is small mv minus capital M v. Minus because they're in the opposite direction, right? Because this is moving towards the left and this is moving towards the right. So this is equal to 0, which gives me small mv is equal to capital M v. So now we have two unknowns, small v and capital V, and we have two equations. So you can try to solve them and you can get the result. By the way, in these example lectures, I'm always going to leave it at, for example, if I have four unknowns, I'm going to write down the four equations and then I'm going to move on to the next problem because I assume that you can solve them on your own. So right now we have, this is my first equation and this is my second equation, and using these two you can solve for the values of small v and capital V, right? Let's see another variation of this problem now. So we have a slightly different variation of this problem. We have, let's say, a block of mass 2 kgs attached to a spring which is initially at its natural length, and we have another block of mass, let's say 1 kg, moving at a speed of 10 meters per second. Unless otherwise mentioned, the ground will be assumed to be frictionless. Okay. So the mass of 1 kilogram is moving at a speed of 10 meters per second towards the block of mass 2 kilogram. It will eventually touch the spring, and when it touches the spring will start getting compressed. Now because the spring will start getting compressed, it will start to push back. So it will push the 2 kg block towards the right and the 1 kg block towards the left. Right? We are asked what is the maximum compression of the spring. Right? That is the question. What is the maximum compression? Initially it's 0. Now let's look at compression in a little bit more detail. I'm just going to draw the spring like a string right now for the sake of convenience. Let's say this is my spring, right? If this end is moving at a speed of 1 meters per second and this end is moving at a speed of 2 meters per second, then obviously the spring is getting compressed, right? But if this end instead of 2 is moving at 0.5 meters per second, then the spring is getting extended, right? So when is the spring not getting extended or compressed? When is it at its minimum or maximum length? We know from calculus that minimum and maximum are achieved when the change is 0, right? So for maximum compression, when this is moving at the speed of 1 meter per second, this should also be moving at the speed of 1 meter per second, right? So the spring will have a maximum compression when it is not being compressed or extended anymore. That is when both the ends have the same speed. Okay, let's call that speed V, right, for both of them at the end. So the first equation will be momentum conservation. 1 into 10 will be the initial momentum. That will be equal to the final momentum. Again, I am taking this combined thing as a system. So the final momentum will be 1 into V plus 2 into V, right? And that gives me 3V is equal to 10, V is equal to 10 by 3. The answers might not come out to be integers because I'm just making these values from the top of my head, right? So we found out V. We need to find the maximum compression. For that we can use the equation of conservation of energy. The initial energy, by the way, this was P initial and this was P final momentum, right? Initial energy is half into 1 into 10 squared, right? The energy of this block is 0 because initially it's at rest and initially the spring is at its natural length, so the potential energy of the spring is 0. The final energy will be slightly trickier. It will be half into 1 into V squared, where V is equal to 10 by 3, plus half into 2 into V squared, plus half into, I'm going to assume K has also been given. Let's say we were given K is equal to 100, plus half into 100 into X squared. We know V, so from this equation we will be able to calculate X, which is the maximum compression, right? So these are the types of problems which we see which involve springs. Okay, now let's look at a problem involving rotational mechanics. So this is sort of related to the banking of roads which you've seen earlier. This is the bending of cyclists on a horizontal road, right? So when you're driving a bicycle and you take a turn, you notice that your bicycle tends to bend towards the side where you take the turn. So we'll try to analyze that. Right, I'm just going to draw a line for a bicycle and we'll for the sake of simplicity, right? So what is important to know is the direction of rotational motion, right? The sense of rotational motion. So this is sort of our road, right? This radius is R and the cyclist is turning on this road, right? And this is the cyclist. He's coming towards you if you're looking from the monitor, right? The cyclist would be something like this. He would be vertical, but we'll see that he bends towards the turn when he starts taking the turn, right? So this is just simply the free body diagram of the cyclist. Now the forces acting on the cyclist are, one is mg acting downwards, right? The other is there must be a force of friction acting towards the right. Mg acts at the center of mass, we've derived that previously. The force of friction will act at the point of contact with the road. The point of contact with the road will also apply a normal force which will end up balancing mg. And since we are working in a non-inertial frame, that is the frame of this cyclist, we will have to apply a centrifugal force, that is the rotational equivalent of a pseudo force. The acceleration of this cyclist is v squared by r towards the center. So the force will be mv squared by r away from the center, right? So this is the free body diagram. And now by balancing the forces, we can see that because the acceleration now is 0, we are in the frame of the cyclist. In the frame of an object, the acceleration of the object is always 0. We say that n equals mg and f equals mv squared by r. Right? We are interested in finding this angle theta. Okay, now we see one more component from Newton's laws of motion which will be added. So in Newton's laws of motion, we made the free body diagrams and we wrote F is equal to ma for a certain number of directions, right? Now we'll start with F is equal to ma, and we'll also use torque is equal to I alpha if it is needed. So in this case it is needed, right? The reason I turn is because this mg is trying to tilt me downwards and mv square by r tends to balance that, right? So we can take the torque about any point. It's easiest to take the torque about this point. Right. So at this point the angular acceleration is 0 since we've assumed that theta is a constant. So the torque about this point is 0. The torque of the normal force and the frictional force is 0 because they're passing through the point of contact. So torque is r cross f and r will be 0 in this case. mg will have a torque of mg. Let me draw this figure more clearly. This is mg acting downwards. This is mv squared by r, and this is theta. The total length, let's take it to be L, it won't really matter. So the torque of mg will be mg into this length, that is, let's take it to be L. If this total is L, this is L by 2. So mg into L by 2 into the angle between them, right? So this is 90 minus theta. Sine of 90 minus theta because it's a cross product, right? So cos theta. What will be the torque due to mv squared by r? It will be mv squared by r into L by 2 into, now this angle is theta, right? So it will be sine theta. And mv squared by r, let's look at the direction of torque also. We talked about that and that's important. The direction of the torque of mg is such that it tries to rotate the object clockwise, but the direction is generally not denoted as clockwise or anti-clockwise. We use the right hand thumb rule. So the clockwise direction, if you use the right hand, will point away from you, away from the monitor. The torque of mv square by r will want to rotate this object in this direction, in this sense, right? And if you curl your fingers around this, the thumb will point towards you. So the torque of this will be towards you. So they'll be opposite. If the two torques add up to 0, because otherwise this object would start moving like a pendulum, we know that these two will be equal, right? From that we get the result cot theta is equal to v square by rg. R is the radius of the turn, g is a constant, v is the speed. So we see that if you're traveling at a certain speed and you're turning along a circle of a certain radius, the tendency will be to bend towards the turn at an angle such that cot theta will be equal to v square by rg, right? So this is a problem which you generally see in standard board examinations. Okay, now let's move on to a problem which is an extension of a standard Newton's laws of motion problem. We've seen the problem of a simple pulley that is attached to two masses before. Let's call this small m. Let's call this capital M. Right? Now, for standard light ropes, we derived a result which was that if the rope does not have any mass, then the tension across that rope is constant throughout. And we used that by taking any small section of the rope, and we saw that since it is massless, the net force on it has to be 0. And since it is massless, mg is not acting on it, so the two tensions on the opposite sides must be equal, right? But that's not really valid when we talk about, let's say, the tension in this rope being T1 and in this rope being T2. That doesn't really imply that T1 is equal to T2. But I told you that T1 will be equal to T2 if this pulley is light. So let's try to derive that and see what happens if this pulley is not light. Right. So let's take this radius to be r. We will assume that the pulley is a disc, not a ring, right? And the pulley, let's say, has a mass m0. Okay. So I'm not going to draw the free body diagrams in this case because it's slightly trivial. I'm sure you know by now. So let's assume this is going down with an acceleration a. By constraint relations, because length of the rope is constant, this will go up with an acceleration a. So my first equation will be capital Mg minus T2 is equal to capital Ma. The second equation will be T1 minus small mg is equal to small ma. This is how we got the value of a and the value of t previously when we took T1 to be equal to T2 to be equal to t. Then we had two unknowns t and a, and we could get the result, right? In this case we have three unknowns T1, T2 and a. Why are T1 and T2 different? Because this object is not massless, right? But now we know how to solve this. So if we look at this pulley, there is a torque acting on this pulley due to T2 in this sense, that is in this sense, that is away from the viewer, and torque acting due to T1 in this sense, that is towards the viewer. So let's draw the free body diagram of this disc. For this disc, we will have a T2 acting downwards, we will have a T1 acting downwards, and let's say there is a T0 acting upwards due to this clamp which holds the pulley to the ceiling. This is not relevant in our question, but it's good to know the forces on every object so that you don't make errors, right? Now we can directly write F is equal to ma, that will be T0 is equal to T1 plus T2. That will give me T0 if I know the other things. That's not relevant right now. We'll use torque is equal to I alpha for this. So let's say this is turning with an angular acceleration alpha. Obviously if the rope is moving, the pulley must be turning as well, right? So in this case my equation will be T2 into R minus T1 into R, that is the net torque, is equal to I alpha. I will be m0 R squared by 2 alpha, because this is a disk and we derived the result previously for the disk that for a disk the moment of inertia is mr squared by 2. So now I've got my three equations, but how many unknowns do I have? So now I have a problem because now I have four unknowns, a, T1, T2, but alpha is another unknown, right? So now I have four unknowns and three variables. It seems like the problem is getting more complicated, but generally this would be true. We do not know alpha and we would not be able to solve the problem specifically, but in problems which you encounter, another specific condition will generally be given. That is, and it will be worded like this: the rope does not slip on the pulley. Right, that means there is enough friction between the rope and the pulley such that if the rope, let's say this point on the rope moves down 1 meter, then this point will move up 1 meter, and not only that, this point, not just of the rope but of the rim of the disc, will also be moving 1 meter. So the pulley as a whole will move on this circumference 1 meter, right? So in that case this acceleration is a, so that means the acceleration tangential would be a, but that would also be equal to alpha r, because we are saying by this statement that the acceleration of the rope at this point is equal to the acceleration of the rim of the pulley at this point. So that will give me a very nice relation, a is equal to alpha r. This is not the standard a is equal to alpha r which we see generally, because generally when we look at a is equal to alpha r, we will be talking about the acceleration of this point on the rim, which is always equal to alpha r. But what we say with this statement is that that acceleration is the same as the acceleration of the rope, right? If the rope is moving, the pulley is moving exactly along with it, right? No slipping is happening. So these give you my four results, and you can try to solve the answer with this and you'll get it. One thing to note, if m0 was 0, then T1 equals T2, right? Which is what we had been using previously, though we hadn't derived it. I told you that if the pulley is light, you can see that even a slight excess of tension on one side will give an infinite angular acceleration to the pulley, right? Because the mass is 0, which means the moment of inertia is 0. So for the sake of light pulleys, we can take T and T to be the same on both sides, but if the pulley itself has some mass and some moment of inertia, then the tension on both sides will be different, right? So this is a problem which we see very often. Let's look at another standard problem. This is a variation of the bending of a cyclist. We have a floor and we have a wall, right? The wall is given to us to be smooth, but the floor has friction, right? And obviously if the floor, and we've put a rod like this at the edge, if the floor would not have friction, we can see by common sense that the rod would just slide to the bottom. But the floor has some friction and it keeps the rod in place like this, right? So what we need to find out is what is the frictional force acting on the rod, right? So I'm just going to draw the free body diagram right here. One is there will be mg acting downwards at the center. There will be a normal force acting upwards, I'll call it N1. There will be a friction and there will be a normal force N2 acting from this wall. There will be no friction from this wall because it's given to us to be smooth. And since the rod is in equilibrium, we can write the easy equations first. N2 equals F, N1 equals mg. We have three unknowns, N2, F and N1. So we need one more equation and we can use that equation of torque. Now here it's very important to figure out what is the point about which we apply torque is equal to I alpha. Remember that this is an inertial frame because there is no acceleration, so we can write torque is equal to I alpha about any point. But in a non-inertial frame we derived that the pseudo force tends to act through the center of mass. So for a non-inertial frame, even if you take it about the center of mass, the equation would be valid, right? In this case it will be valid everywhere. Let me take three special points, this point, this point and this point. It wouldn't make sense, it wouldn't make a lot of sense to conserve the torque about this point or this point, any random point. These three are special points, right? If I conserve the torque about this point, if I equate the torque to 0, in other words about this point, I would get three terms. The torque due to N2 would be 0 because remember torque is R cross F, and if R is 0, torque is 0. So the torque of N2 would be 0. We would have three different torques, N1, F and mg, right? If I took it about mg, again I would have three terms, N1, F and N2. But if I took it about this point, then the torque of N1 and F would be 0 and I would have only two terms. It makes it easier, right? So I'll equate torque to 0 about this point, but I would suggest that at home you try it about any random point, even a point midway between these 2 points say, and you should be able to verify that in every case the answer will be the same, just the equations will be slightly more complicated. So the third equation will be conservation of torque about this point, right? So let's take the total length of the rod to be L, let's take this angle to be theta. Those things will be given to us in the question. So the torque net will be mg into L by 2 into, so this is mg, this is L by 2, this is 90 minus theta, the sine of 90 minus theta because we are using the cross product. So cos theta equals N2 into L, now not L by 2 because this is L, right, into this angle is theta, so sine theta. So now we have three equations and we have three unknowns, F, N1 and N2, and we can solve for any of them. We can get N2 directly from this, that will be equal to F, and N1 is equal to mg directly, right? So we see that while solving problems of rotational motion, we've just added one or two new concepts to Newton's laws of motion. We draw all the forces, draw the free body diagram, write the acceleration and the angular acceleration, take F is equal to ma. But right now we've also added one more thing. We also take torque is equal to I alpha if needed. If we have 4 unknowns in the question, we need 4 equations to solve it, right? If you have 7 unknowns, we need 7 equations. I've seen questions as far as 8 unknowns for which you need 8 equations, but for your courses you won't generally have more than 4 unknowns, right? Now let's look at a problem which might confuse you a little bit, right? So we have a rough floor, now it's not smooth, now it's rough. On that we have a sphere, a solid sphere, and a force F is acting along the tangent, right? So what we are told is that, and we've discussed this previously, that what is occurring is rolling without slipping. If rolling without slipping is occurring, that means the velocity of this point on the ground has to be the same as the velocity of this point, right? Otherwise there would be a slipping. That doesn't mean if there is no slipping there will be no friction. We discussed a third type of friction which will act, which is rolling friction, right? So the object is rolling without slipping. We are given the mass and we are given the radius and so on, right? And we need to find out the magnitude and direction of the frictional force acting, right? So let's just take the frictional force to be this, right? Let's take the direction to be the left and take the magnitude to be m. The first equation will be small f, capital F minus small f is equal to ma, right? We assume that the center of mass is moving with an acceleration a. So F minus F will be equal to ma. The second equation we'll use is torque is equal to I alpha. Now remember, this is interesting. The force is opposite in both these cases, but the torque is the same. This F wants this object, this sphere, to move in this sense, and this friction also wants it to move in this sense. So the torque due to both of them is acting in the clockwise sense, that is away from the screen of your monitor. So their torque will add up. So Fr plus small fr, we don't need any sine theta because it's perpendicular. This into sine of 90, this into sine of 90, right, is equal to I alpha. We know the I for a solid sphere, it's 2 by 5 mr square. Right, we didn't derive it, but you can try to do it yourself. Alpha. So we have unknowns f, a, and alpha. And we have only two equations. We need one more. The third equation we'll get from the constraint relation. Let's say the center of mass is moving with an acceleration a, and the angular acceleration is alpha. So what is the acceleration of this point? The acceleration of this point will be the acceleration of the center of mass plus the acceleration with respect to the center of mass, right? The acceleration of the center of mass is a towards the right. What is the acceleration of this point with respect to the center of mass? If I'm sitting on the center of mass, I don't see the linear motion. All I see is this rotational motion happening, right? So in that case, it will be minus alpha r, right? Because alpha r will point towards this direction, and that a has to be 0 because there is no rolling. There is rolling but without any slipping, right? So this point and this point have the same speed and acceleration always. So that gives me a equals alpha r. Three equations, three variables. Let's try to solve them, and the reason will be clear in a second. So the first equation basically gives me f minus f is equal to ma. The second gives me f plus f is equal to r alpha. I can write it as a. The 2 by 5 mar, r cancels, 2 by 5 ma. We can add the two of them and we can get 2f is equal to 7 by 5 ma, or we get f is equal to 7 by 10 ma. From that we get small f is equal to capital F minus ma, that is minus 3 by 10 ma. Now this is an interesting result. So what we derive is that the magnitude of the friction is 3 by 10 ma, right? But the direction of friction is actually towards the right in this case. So again, we do not always go by what is the motion of the center of mass. We look at the motion of this point, and the motion of this point is basically 0 because this is at rest. If this is at rest, how do we see the direction of friction? Either we can solve it like this, or we can just simply try to look at what would be the motion of this body if there was no friction, and you can try it at home. If there was no friction, this F would cause the body to go forward with an acceleration a, but this F would also cause the body to rotate about the center of mass with a particular angular acceleration. And if there is no friction, the angular acceleration will dominate and the speed of this point will actually be towards the left. Hence the friction is towards the right. Right? So this is an important concept, that when there is no relative slipping, the best way to calculate friction is to see what is the direction of motion if there was no friction, and it would be opposite to it. Right? So we've seen many different examples of this. I hope this has made you clear. In the next lecture, we will see some concepts and examples up till everything we've done till now in the first 5 units. And I'll introduce only advanced concepts and examples which are not generally used in your board examinations but might be used in harder entrance examinations, or if you simply wanted to learn some advanced stuff, right? So there will be extensions of these concepts, but those which you will not necessarily need to be using, right? Thank you.